So in this video, our goal is to answer the following. Find the remainder when 1 raised to 51 plus 4 raised to 51 and so on until plus 2601 raised to 51 is divided by 101. So before we start, I suggest that you first try this out on your own before you proceed on this video. Okay, good. So let's begin. So we have here our solution. To start this problem, let us first denote this thing here. Oops. This thing here, let's denote it as S to denote sum. First, observe here that in S, all of the terms here are raised to 51. Moreover, this one, the base is 1 squared. 4 here can be written as 2 squared. 9 here can be written as 3 squared, and so on until 2601 here, take note, is equal to 51 squared. So given that fact, again observe that S is just equal to the sum of k squared raised to 51 from wherein k is from 1 to 51. By laws of exponents, let's just write this better. By laws of exponents, this is just equal to so the exponent can be multiplied, so we'll have 2 times 51, or just simply k raised to 100. So this is our first key observation. Now in problems like this, take note that we can actually restate this part divided by 101, the remainder, by using the concept of modular arithmetic. So let me write that one down in notation. So essentially, our goal here is to obtain S modulo 101. So basically, in modular arithmetic, what it does is this mod 101 is basically what you divide with. So in our case, 101. And then this operation gives us the corresponding remainder. So this is what we'll be applying, and more specifically, we'll be applying some of the properties of this modular arithmetic in this problem. Aside from this, we'll be using the following famous result. So in number theory, this is a famous result. It is called Fermat's Little Theorem. So what Fermat's Little Theorem states is that for any integer a that is not divisible by p, wherein p here is prime, so let me write it out here, we obtain the following congruent. So a raised to p minus 1 is congruent to 1 modulo p. So this is what we'll be using in this problem. So in our case, since we have mod 101, and you can check that 101 is actually prime. So since 101 is prime, then by Fermat's Little Theorem, then for any k, so in this case, instead of a, we'll be using k here, because our k here represents the k out here. So for any k from 1 to up until 51, we get that k raised to 100, since 101 minus 1 is 100, must be congruent to 1 modulo 101. Or essentially, the remainder of k raised to 100 is just 1 when you divide it by 101. So given this fact, and applying some modular arithmetic stuff, so hence, we'll actually obtain that k raised to 102, this can be written as k raised to 100 times k squared, but by modular arithmetic, we know here that this thing is just congruent to 1 modulo 101. So we'll have here 1 times k squared, which is again just equal to okay, let me just write this one as k squared modulo 101. So essentially, the k raised to 100 here became just 1. Okay, so let me just fix this a little bit, the spacing. Okay, using this fact here and going back to what we have out here, we obtain that s here must be congruent to the sum from k equals 1 to infinity of k squared modulo 101. Or basically, the purpose of Fermat's Little Theorem here is changing the problem from examining k raised to 102 to just k squared. So the remainder of the two basically is the same. When you, oopsies, this is not infinity. This one is 51. There. Okay, there I go. So that is the purpose of like the Fermat's Little Theorem again. And this is what modular arithmetic do. Instead of treating this bigger stuff, we can just treat this and they will have the same remainder by modular arithmetic. And what is good about this? Well, we actually have a formula for the sum of squares. So that is the next key fact in this problem. So let me just write it out here. So next key fact is the sum of squares. So what we have here is that take note that the sum of k squared from k equals 1 to n, wherein n here is any natural number, is just equal to the following rational expression. So we'll have here n times n plus 1 times 2n plus 1 raised to 6. So again, this is true for any n in n. Okay, let me just write this one better. Okay, good. So in our case, since 51 here is the n, so n here is 51, then by the formula, so the formula for n equal to 51, the sum of k squared, k equals 1 to n, is given by, this is 51, apologies for the errors again. So this one will become 51 times 51 plus 1 times 2 times 51 plus 1 all over 6. Then I'll just leave this to you to verify. But this would actually, this can actually be simplified to 100 times 442. Now from here, note that we split these two because we'll examine it individually. Yeah, so first, take note that 103, when you divide it by 101, clearly the remainder is just 2. On the other hand, 442, take note that you can actually write this one as 4 times 101 plus 38, which means that when you divide 442 by 101, the remainder must be 38. So this is like dividing by 101, this is the remainder. And then from here, take note that by property of modular arithmetic, it actually follows that, this is the color again of s, that s, so again, going back, s is this, which we simplified to this thing, then by modular arithmetic simplified to this thing, and then by using the sum of squares simplifies to this thing. So take note that s is actually congruent to, let's see, let's put here the mod 101. It's congruent to, so the 103 here can be replaced by 2, And then the 442 here can be replaced by 38. And then property of modular arithmetic, you can multiply these two, and this one will be congruent to what it's supposed to be in the first place. So simplifying 2 times 38 is the same as 76 modulo 101. And then take note that 76 is less than 101, which means that 76 is already actually the remainder that we are looking for. So therefore, concluding with this problem, the remainder we are looking for is 76. Yeah, there. So the remainder that we are looking for is 76, and that answers the following problem. So yeah, I hope you enjoyed that one. If you have any suggestions, any video for the future, just comment it down below and I'll be happy to comment and react on it. So yeah, that's about it. Have a nice day.